All known elements are organized onto the periodic table of elements, the single most useful cheat sheet ever developed. It is extremely rich with information once you get to understand the layout. Each box on the table refers to one element and contains useful information about that element. The biggest part in each of the boxes is a 1 or 2 letter designation. Most are easy to understand, like H for hydrogen, C for carbon, or Ra for radium, but others like potassium, mercury, or antimony aren't as obvious. Since some elements have been known since antiquity, like gold, the symbols sometimes refer to historic or Latin names. An element is defined by the number of protons in its nucleus, so the atomic number is equal to its protons, from 1 proton for hydrogen to 118 in oganesson. Now that's sensible enough, but why are the columns arranged with big gaps between some of the elements? Now this is all because of quantum theory. Neutral atoms must have the same number of electrons as protons to balance out the charge. Electrons are only stable in an atom if it's inside an orbital, the 3D shapes controlled by the first 3 quantum numbers. The orbital energy is defined by the principal quantum number n, and these form the rows. So the first row on the periodic table is n equals 1, the second row is n equals 2, and so on. The orbital shape is defined by the angular quantum number L, that can only go as high as n minus 1. So where n equals 1, L can only be 0, and that's what we call the s orbital. So the first row of the periodic table is restricted to principal quantum number 1 and an s orbital, or 1s orbital. The magnetic number determines how the orbital shape is oriented in space and ranges from negative L to positive L. S orbitals are spherical, and since there's only one way to orient a sphere in space, there's only one s orbital. Also, negative 0 to 0 is just 0. There's only one magnetic number. Spin doesn't affect the orbital size or shape, but it does allow each orbital to be filled with 2 electrons. So the single electron in a hydrogen atom is in a 1s orbital, and so are the 2 electrons in the helium atom. Helium's second electron completes all the possible electrons that can fit into the n equals 1 orbitals. So helium completes the first row. On the second row, where the principal quantum number is 2, we can have angular momentum numbers 0 or 1, or both s and p orbitals. There's still only one s orbital, but p orbitals can take 3 orientations along the x, y, and z axes. Notice that from negative 1 to positive 1 is 3 numbers, negative 1, 0, and positive 1. That's 3 magnetic numbers, 3 p orbitals, each with 2 electrons. So if we're counting, that's 2 electrons in the 2s orbitals and 2 times 3 electrons in the 2p orbitals, for a total of 8 electrons in the second row. The third row follows the same trend, but should it? Shouldn't we get a third type of orbital in the third row, just like we did for the first 2? Well, that's why it's called a periodic table and not the quantum table. When arranged by the number of protons and principal number, each column or period shares chemical characteristics. That's why we can give names to the groups like the halides, because they make salts, or the noble gases that are non-reactive gases, and why the metals and the non-metals are all grouped together. We can also read the lowest energy electronic states directly from the table, which is what we'll demonstrate next.